Alright, so what we're gonna do today is just go over the class lectures and I'll try to explain some concepts to you guys. We're gonna start from the class lecture notes, page 47. First example is a NAND 2. Okay. NAND 2. In this case, we have we're asked to design this gate using CMOS transistors. Okay, the way I approach this is as follows. You have the operator AND here. Okay, AND is the operator. So you take note of whatever the operator is. Okay, so in other words, this is something like this, right? But it's not, right? Or this is also right. Let's call it AB. So in this case, the operation is ANDing and then nothing, but the main logic is just ANDing. So the way I approach to designing CMOS transistors for various logics such as NAND would be as follows. I'm going to look at the operator, it's AND. AND means that there is a concatenation. As you could see, A and B are concatenated, right? So my NFET tree is going to be concatenation of two transistors, and then I'm going to pull my V out. Okay, and then I'm just going to take whatever I had here and write it in the opposite form. So if I have concatenation below, I'm going to have some parallelism above, right? If I have some parallelism down here, I need to have some concatenation up here, right? So if I have A and B here, these, you need to know, are connected to VDD. Okay, so they're able to capture the high voltage and supply it at the output. Okay, this is connected to ground. These are PMOS transistors, these are NMOS transistors. We're looking at the NAND, which is ANDing 2 and nothing. Okay, and if I have the main operator as AND, I realize, I say, hey, wait a minute, this is concatenation, therefore it has to be parallel up above, right? Okay, so the next one, it's a node. Okay, let's look at the next one. Next one is a node 2. Node 2 is also A or B not, right? Which could also be represented as follows. Right? So the main operation here is the ORing, right? This is not the XOR, but it's an OR. Therefore, you say there's a parallelism down below at the NFET tree, not the PFET, the NFET tree down below. So I take the two, put parallel, they're connected to ground. Okay, and then for my output, and then whatever it was here, as you'll see, for example, for this case, it's parallel up here, it has to be series up here. They're gonna get kind of messy as you go along, but if you understand the basic idea here, it's very simple to tag along and ace the final. So, okay, node 2 here, NAND 2 here. And then, what page 47 does is it goes through the truth table for each of these guys. So let's just go through the truth table for a NAND 2. Okay, I'm just gonna write it here. Let's write it here. A, B, and V out. Okay, 0, 0, 1, 1, 0, 1, 0, 1. I mean, you could approach in any way. you could go by testing your knowledge through this guy here, or you could go about it by giving these values to this guy. So let's just go by giving 0, 0 to A and B and see what happens. If A is 0 and B is 0, these transistors are on. We're going to take this voltage and supply it out. Therefore, V out is going to be 1. If A is 0, B is 1. If either one of these, at this point you have to be able to realize that since there is a parallelism going on, you need to know that no matter which one is on or which one is off, as long as we have either one of these guys on, you're gonna get a high output. Okay, therefore this is going to be 1, this is going to be 1, this is going to be 1, and then we come to 1, 1, 1, 1, we'll turn off the PMOSes. Therefore low voltage is on and we get a 0. Okay, and for the NOR case, you have A, B, and V out. Okay, let's just test our knowledge and just say for 0, 0, I think there's a mistake here. So we get these guys here, and these guys are PMOSes. Okay, so this looks better. And remember, whatever the operation is, you take and start with the NFET tree, and the NFET tree. NFET tree, reverse it for the PFET, reverse it for the PFET. 0, 0 is going to give you what? It's going to give you 1. Okay, 0, 1. Just pay attention to this step. 0, 1 is going to give you this device is on, this device is off. So since 0 is not going to pass, 1 is not going to pass through, it's like this, you know. It goes through, but this switch is on here. It goes through, but this switch is on, so you can't get high voltage at the output. Therefore this one is also 0, this one is also 0. Okay, but as soon as you see this 0, 0 being 1, you need to be able to realize that if either one of these are going to be off, I want to have 0 output. Okay, so at this point we're able to go on and build more complex circuits. So please continue with video number 2.